start. So, Şener, would you please close your video? Yes.
Sure.
Okay. Hi, everybody. Good afternoon. First of all, I would like to thank the organizers of COVID-5. This sixth session of COVID-5 will be started. And our first speaker is Theodora Kirova from University of Latvia. She is going to talk about ultra-high precision right-bite atomic localizations using standing waves and optical vertices. So please, Theodora, thank you for your coming to.
Thank you very much. I will try to share now my screen. Let me know if it's working.
Yes.
Oops. So hi everyone. I'm very happy to be here at COVID for a second time, and thank you for accepting my talk as a short talk. So I will talk about our work that we did with some colleagues from China and from Iran and from Lithuania about how we can precisely or ultra precisely localize Rydberg atoms using standing wave and optical vortices. So just in the beginning to remind everyone again why Rydberg atoms are so interesting, because they have large sizes, small binding energies, also very long radiative lifetimes of the order of microseconds. Also, they have big dipole matrix elements, which means that they interact very sensibly with electric fields, and also they interact between themselves with dipole-dipole interaction. And due to all these properties, Rydberg atoms are very interesting for applications in many body effects, outer core plasmas, condensed matter, and quantum information. Also, another useful phenomenon in Rydberg atoms is the so-called dipole blockade, which was predicted by Lukin, and then a lot of experimental groups, for example, like the one in Pierre Pierre's group in 2009, have showed it experimentally. So what is dipole blockade? Imagine that you have a Rydberg atom, which is connected to intermediate state and also to ground state. And imagine that you want to excite it with your laser. However, due to the dipole-dipole interaction, your laser is actually off resonant, and it cannot excite your Rydberg state, due to which this excitation is impossible. And this is what is called dipole blockade. So, for example, in this experiment in Pierre's Pierre group, when they keep the atoms at a bigger distance, they can see single atom excitation and also double atom excitation. But when they bring the atoms together, then the double atom excitation is subdued, which means that we can observe the dipole blockade. Also, another useful phenomenon is the so-called anti-blockade, in which you can actually compensate for the dipole-dipole interaction shift using detuning of your laser. And this is some work by Vaidemillo's group from 2020, just to see that when the dipole-dipole interaction is compensated by, in this case, he's using autotrans effect, so by the Rabi frequency, then the double excitation is actually possible. Another useful phenomenon, which is adequate for what I will be speaking about, is EIT, or electromagnetical induced transparency. Already a lot of speakers talked about it, but just to remind everyone, Basically, the first experimental realization is in a lambda scheme. So you have a pro field and a stronger coupling field, and due to interaction, due to interference between those two fields, it happens so that the pro field becomes transparent, the medium becomes transparent for the pro field, and you can actually see transmission of the pro field when the coupling field is turned on. And theoretically, EIT can be explained by the creation of a dark state, which is combination of the two ground states. And the condition for EIT is that there should be some certain condition between the coupling field and the tunings and the and the spontaneous emissions in the system. So to go to, after this introduction, just to go to the work that we have done, theoretically, the first scenario that we looked at is how to localize Rydberg atoms using a standing wave. So we have Rydberg atoms arranged in a so-called ladder scheme. So you have ground state, middle state, and Rydberg state. The first step of the ladder is interacting with a traveling wave pro field, and the second step of the ladder is interacting with a standing wave field. In this situation, we can write the Hamiltonian of the system. It consists of the unperturbed atomic Hamiltonian, the atom field Hamiltonian, and also, of course, the dipole-dipole interaction between the Rydberg states. Also, with this Hamiltonian, my colleagues have derived this analytical expression for the steady-state solution of the Rydberg population. Of course, it depends on the position X, because we have the coupling field is a standing wave. And also we have, which is important, this parameter S, which describes the energy shift to the Rydberg state due to the dipole-dipole interaction with other atoms which are beyond the blockade radius. My colleagues also derived equation how this S looks like in terms of the parameters of the system. And we have a parameter zeta, which basically shows us if the system is, if the distance between the atoms is smaller or bigger than the blockade radius. So if you want to achieve localization, that means that the Rydberg population should be equal to 1. And for this to happen, we need the condition delta S minus S equals 0. And then actually this could happen in two cases, either at the nodes of the coupling field, or we can also say that it happens at all cases. So depending on that, depending on how the Rydberg level energy shift induced by the dipole-dipole interaction is compensated by the coupling field tuning, we have two anti-blockade regimes, the partial anti-blockade, in which this compensation happens only at the nodes of the field, and full anti-blockade when this happens at all points. So we have made calculations for two different Rydberg states. One is the 60S1/2, and one is the 30S1/2. They have different lifetimes. And the 60S1/2 is longer lived. And we have calculated what is the time for which the system reaches a stable, steady state situation. And so we have two times for each of those states. And then we have plotted the dependence of this time for reaching the steady state as a function of K, and K is the ratio between the coupling field strength and the probe field strength. And we can see that in the case of full anti-blockade or partial anti-blockade, we can get different situations for which, in order to reach the steady state, we have to have a certain K number in the system. So we're basically trying to find the best parameters in which we will reach this localization. So the important points here are these green points, in which, depending on the K, we can get the time that we need. And knowing the parameters of K that we need for the system, we can calculate the steady state Rydberg population, and we can see as a function of the distance, and we can see in which case we get the localization. So again, we can do this for the different states, 60s½ and 30s½ and we can also do it in the case of different parameter, etc., and in the case of full anti-blockade and partial anti-blockade. And we see that the best case for reaching this localization is this one, especially in the case of partial anti-blockade. So if we use full anti-blockade, then we can get for which have maximum of the localization to 0.6 nanometers. And for the parameters that we're using, and in the case of partial anti-blockade, we can get even smaller full width have maximum to 0.56 nanometers. And to continue with the case of,
yeah. Sorry, last 3 minutes.
Thank you. To continue to the case of using optical vortices for localization, we use the same scheme, but instead of standing wave, in the second step of the ladder, we have a optical vortice, which looks like this. And in this case, we can show that depending again on the parameter K, when K is really big, which means that we have a really strong coupling field, we can get a very small localization with the full width have maximum 4 nanometers for L equals 1. And if we increase the L number of the optical field to 5, for example, then this localization becomes worse. And finally, so what I showed you before was a 2D localization. Finally, we can also get 3D localization if we apply a spatial modulated two-photon detuning, which is like a sine function. And then in this case, depending again on the K number, we can get a good localization. And again, it depends on whether we have partial anti-blockade or full or the partial anti-blockade condition is broken. So this just shows us that this anti-blockade condition is really important in order to reach a good localization. So finally, to conclude, we have theoretically proposed different scenarios, and we have done some calculations showing that using standing waves or optical vortices, we can get to nanometer or sub-nanometer scales localization, depending on full or partial anti-blockade regimes. And in the cases of optical vortices, we can also get a 2D or a 3D localization. And I would like to thank the Cost Action Quantum Technologies with Record Atoms for basically supporting my research. Thank you for the attention.
Oh, thank you for a nice presentation. Is there a questions? One more question from Sevilay Sevinçli. Is there a real interaction for the case of 30 seconds? It's a practically non-interacting, right? Is it?
Let me see. You mean for this one? I'm not sure I understand the question, but basically,
third state.
Basically, we are in
30S state, 30S state.
30S one. For this one. This one is it's not so stable. I mean, the 6DS one half is metastable. This one is not so stable. That's why we don't get so good in localization. We get this case, and it's not working so well. So it's really important that the upper state is stable.
Is there any questions? So thanks again to Theodora Kirova. And
thank you.
One more question. So the second speaker, Şener
So
Özen.
I stop here.
Yes. Our second speaker, Şener Özender from İstinye University. He will give a talk about physics and machine learning reunited. So please, Şener.
Thank you very much. Hi, everyone. Thank you very much for invitation. My name is Şener Özender. I am a faculty at İstinye University in Istanbul at the Electrical and Electronics Department. So what I will talk about today is the connection and the long common history between physics and machine learning. So the aim of this talk is twofold. So this talk is for physicists and also for machine learning people. So first of all, we can describe machine learning in physics language so that physicists learn more about machine learning. We can talk about models of magnetism, which I will in this talk, renormalization group, partition function, and other ideas from statistical physics, how they are connected to machine learning. And we can also talk about physics foundations of machine learning. So physicists would be interested in this part. So how the ideas from physics, such as entropy, Kullback-Leibler divergence, restricted Boltzmann machines are used in the machine learning so that physicists can be interested in machine learning as well. So analogies and cross-pollination between the two disciplines, they have been happening for a long time. So we can explore these analogies a bit more, starting with this talk today, maybe. And concepts used in physics may also serve the artificial intelligence community. So let's get started. So how can physics help? There are some problems in machine learning. I think physics and physicists can help to solve some of those problems. First of all, what we can do is we can draw connections between physics and machine learning and exploit those connections. In the following slides, I will talk about the relationship between statistical mechanics and the machine learning model, the two-layer neural network model, which is called restricted Boltzmann machines. They are definitely inspired by statistical physics. Or what we can do is we can also find maybe dualities between deep neural networks and some easy problems to reduce the cost of training deep neural networks. Some of these networks are trained by spending millions of dollars, just like the recent GPT-3, the natural language processing NLP model. So instead of spending those millions of dollars, maybe we can make dualities between neural networks and physics, easy physics problems that we know how to solve, and then we can help maybe AI community. How do dualities work? Physicists definitely know how they work. For example, you have a hard problem here. It may be a strongly coupled four-dimensional quantum field theory, which you cannot solve because there's strong coupling. What you can do is you can map the problem to a weakly coupled five-dimensional theory. It's gravity theory. And then solve it here, which is easy to solve here. And then you can map the solution back to the original problem. So we can maybe find dualities between machine learning or in general artificial intelligence and physics. So all of physics is about minimization or maximization of some objective function. So in this case, what we have is the Lagrangian is our objective function. The term objective function is often used by the machine learning practitioners. So it's the function that they want to minimize or maximize so that the neural network it gets trained. So in our case, I mean, even the refraction of a light, it's a minimization problem. So what we have is usually Lagrangian, which includes the kinetic and potential terms, and we minimize it. We find the path of the particle or a light ray, whatever it is. Or in statistical mechanics, we have the free energy, and we try to minimize this to find the equilibrium point. And again, in statistical physics, we have Gibbs entropy. You can have the probabilities, and you can even have some constraints. In this case, the probabilities should add up to 1, or you can have another constraint for the energy, which I will show later. So these, depending on the entropy term that you have, it just looks like the Lagrangian. You can have microcanonical, canonical, or grand canonical ensembles. And this term is, by the way, if there's any machine learning practitioner, it just looks like Kullback-Leibler divergence. So also in chemistry, computational chemistry or computational physics, we still want to, again, minimize the energy. So we are looking for, let's say you want to calculate the energy states of benzene ring here. What you would do is you would run a DFT, density functional theory calculations, and what you would try to do is you would look for the electron density that would minimize the energy. So basically, physics is all about minimization. And I will talk about minimization in machine learning later, but let's go with physics for a bit more. So most machine learning models, this is another problem that machine learning field has. They are black boxes. What it means is you train the network, the performance is 99.9, but it works well, but you don't know how it works. So that's a problem, especially if you want to apply that machine learning models in, let's say, in medicine. You want to know how the neural network works. So they're not explainable. So can we reach physics explainable AI? And as we know, explainability is the job of physicists. We see some data, we make some primitive models, and then we improve the models and we reach the explanation. So if there's one thing that physicists detest the most, I would say it's probably black box models. We don't like them. Machine learning models are highly susceptible to even noise. Let's say you train a model, and this is a duck, a picture of a duck, and so after you train the model, let's say if you show this image, it says it's a duck. Okay, that's good. But if you add even 7% of noise, it's pretty small, then the prediction of the machine learning model is this is a horse. So that's a problem. So they are highly susceptible to noise. Or you train a model that recognizes audio. Let's say you have the clip of audio, how are you? And you add 1% noise, and the machine learning model takes it as open the door. Or in this picture, you can see that if you have a picture or painting like this, you can easily fool the machine learning model. Okay, so the question that I want to arise here, can topology help solve the robustness problem of machine learning? 2016, Nobel Prize went to topology. So the basic idea of topology is they are robust to continuous deformations. For example, the topology here for these two objects is 0. The topological number for these ones is 1. The reason is that you can wrap some thread here or here. So there's basically just one hole. There are two holes here. One of the holes is here, the other is here. So what you do in condensed matter physics typically is let's say you want to calculate the hole conductivity, and you usually have a phase term. You take the integral, and the integral is always, this integral is always in multiples of integers. So the nice thing here is, so by the way, this is coming from the wave function in the system. But the nice thing is here, even if you deform the boundaries or the system, this quantity doesn't change. It's always integer. So, and the same here, you can deform this or this. So you can think of these as the deformed versions of each other, but the topological number or feature doesn't change. So, okay, so can we go beyond local pixel-based filter convolutions? That's what most machine learning models use when they are trained with image data. But can we go beyond them, and can we use global topological features? One of the funny problems that machine learning models have is that they confuse Chihuahua and Muffin. So you can see that the machine learning, the performance is really bad in these cases. But maybe there is a way, by using the ideas from topology, we can maybe cure this problem. Okay, so now I talked about a little bit machine learning now, and also physics. Now let's move to condensed matter or solid state physics a little bit, and then we will make connections between these two fields. So some materials are magnetic below a critical temperature. If you cool down below TC, that TC may depend on the materials, and they become magnetic. They attract metals, and above that TC, they become non-magnetic. So the spin-spin interaction energy favors spin alignment. So the energy or the Hamiltonian is written like this. Of course, there's a sum here for each term, for each couple. So the energy, because of this negative sign here, the energy favors spin alignment because this is a lower energy state. But what heat does, it randomizes the spins. So that's the entropy, and it favors random spin orientation. So there's a trade-off between energy minimization and entropy maximization, and you know that free energy is average energy minus TS. So okay, so material becomes magnetic below TC. So there's an average spin below TC. This is average spin. You can think of it as magnetization as well. So it's non-zero below TC. And right at TC, there is a phase transition. So above TC, you have just random spins like these. These particles here simulate the temperature, the ambient temperature. So they hit these spins, they randomize them, so they create entropy. So above TC, well, the average is basically 0. But as you go below TC, so if you're far away from TC, below TC, then you get non-zero magnetization because most of the spins now, the temperature effect, the effect of these guys, they would create entropy and randomization. So they are low at low TC. So you would get an ordered state with net magnetization. And if you go to 0 temperature, you get magnetization or average spin to be 1. So there's a phase transition at TC. Okay, so spin wants to align to minimize the average energy. And if you write down the Hamiltonian for this setup, for example, so the spins are, all neighbors, the spins are in opposite directions. So you would get -1 from each bond. So you would get ultimately 4. In this case, the Hamiltonian is, or energy in units, 4 units of energy. Now, but the ambient heat or temperature wants to randomize the spin directions. Now, this is quantified by the entropy term. So in this setup, if you insist on this energy, that energy is 4, then there are 2 possibilities, and the entropy is basically log of multiplicity of states, which is in this case log 2. Now, free energy is, it becomes minimum when the thermal equilibrium is reached. Free energy is analogous to the objective function in machine learning, such as Kullback-Leibler divergence. So when the free energy is minimized, the final spin positions, so some of the spins are up and some down, so they are analogous to the weights learned in artificial neural networks. So if you train a neural network, this is the input layer, this is the output layer. So you feed the network with a bunch of data, and when it learns, what it learns is basically the weights between the nodes. So when you have these numbers, then you can say the network is trained. Now you can use that network to make predictions. So, but we are not interested in the states of spins at the individual level, right? I don't really care about if this spin of this spin is up or down. Or in the neural networks, I don't really care about the particular or individual weights. What I care about, the observables, which are macroscopic variables like magnetization, just spin average, temperature, energy, etc. In the context of neural networks, the corresponding variables may be output layer as the weighted average of hidden layer. So here we calculate the we take an average of spins. It's a simple average, just arithmetic average. In this case, you do this, you do a similar thing, but you average over these weights. So what you're interested in here is basically the output layer, not the individual weights. So how does magnetization change with temperature? Let's talk about this. So this is the free energy, and this is the average magnetization, or the average of spins. So if a spin is up, then you can think of it as 1, down is -1. If you are at high temperature, let's say 2.4, TC happens around 2.2, 2.3. So you're above the TC, your free energy is something like this. So the minimum of this free energy at this temperature is this point. That means the spin average or magnetization is 0. And what happens if you go to colder temperatures? Let's say you go below TC, let's take this one. Now your free energy is like this. So you are either here or here at one of these minimums. So this minimum is like all the spins are down, and this minimum is for all the spins up. So the point here is that thermal equilibrium free energy is minimized. Okay, so let's slowly go into the ideas of entropy information, and they will be useful for the following slides. So here we have it. So again, think about blacks as down and white cells are up. So you can think of +1, -1. So at high temperature, what you have is the free energy. So this is high temperature, completely disordered. So the average magnetization is 0. So here we are at high temperature, it's disordered, random, untrained. So this is a term from machine learning, and the average is 0. The information here is incompressible. I cannot really compress this information. I have to keep it like this. This is a noise. You cannot compress noise. Complete ignorance, because information is not, it's not compressible. So each spin can be up or down. There's a complete ignorance here. So the entropy is, you can calculate entropy for each spin case, and you find log 2. So this is a high entropy state, high information content. Now, if you go to low temperature, below TC, what happens is you are one of these minima. So here we have almost all spins down, but there are a couple white ones, so you can think of them as up, but the magnetization is -1 or almost -1. This is a low temperature state. This is ordered, trained, and the average is -1. Information here is incompressible. If I want to talk to you about this state, I can say it's black and there are a couple whites, and you can actually calculate entropy here. It will be lower entropy because there are only so many points that you can place these white dots. Here there are just too many points, but here is less points. So there's complete knowledge. Each spin is down if, well, this happens at t equals 0, definitely. And at t equals 0, the entropy is 0. That's a low entropy state, low information content. Okay, so let's talk about traveling salesman problem. So, and I will say that learning in machine learning or any algorithm, it's actually cooling. So the idea here is there's a salesman, he has to go to different states, sell different certain products. So what is the shortest path for him? So you run a simulation. So basically you're trying to learn the optimum path. And in this case, learning is cooling down because you simulate this by using a fictitious temperature. It's not real temperature, but you call it temperature. Temperature is decreased with small steps to reach the minimum of the cost function. And you define it, sorry, you define the cost function as the minimum distance or the distance. When it's minimized, then you get the minimum distance. So it's the total tour distance. And learning rate here, which is again a term from neural networks, it's the step size here at temperature. And you can see here that there's a temperature. It goes down. Again, this is a fictitious temperature. It goes down with iterations. So the system learns, and as the system learns, the distance, the tour distance goes down. So this is the point where the algorithm learns. Okay, so Isaac model, we talked about it. It's not very interesting because the free energy minimum corresponds to all spins up or all spins down. So all spins up or all spins down when it learned or when it goes to the ground state. This is not interesting. So what's interesting is, and oftentimes people make connections between machine learning and the model, spin glass models. This spin glasses are, they happen in various materials such as silicium oxide. So spin glass model, it has a richer structure. The minimum energy states correspond to rich spin configurations. So now here, Jij's, the interactions between spins are not the same. Here they were the same. So J was equal to 1 here, but here those connections or interactions are different. So for each spin, I have a Jij in the Hamiltonian. So when this system cools down, when you find the ground state energy, it's not like Ising model. So you can have spins in different directions. Now, the learning here is basically what you learn in this model is the directions of each spin, and it corresponds to the weights learned in the neural network. And if you look at the free energy of the spin glass model, the ground state is interesting. The ground state doesn't have just like 2 minima, it has multiple minima. And I will talk about how this is relevant to machine learning, probably in this slide. So the question is why deep learning doesn't get stuck to a local minima during training. Why does it find the minimum so effectively? Deep learning models are so effective. So the reason is that there are billions of weight parameters. So here, of course, you see just 2 hidden layers, but usually there are thousands of layers, millions of nodes. And so there are billions of weight parameters in deep neural networks. So flat directions or saddles are abundant in 1,000-dimensional loss space. So even if you are, even if you, let's say you cool down, you train the network, you stuck in this local minima, but there's always another direction that you can continue. So of course, if you do a training in one dimensional, there's a possibility that you will get stuck here. But if there are multiple dimensions, you can always go those directions and continue to find the ground state. So this is the reason why deep neural networks work so well, because they have millions of parameters. Okay, so let me talk about restricted Boltzmann machines. So probability of a specific configuration at temperature T is given by the Boltzmann distribution. We know this from statistical physics, where the energy in this case is given by the spin pairs. So this is the most likely configuration at low temperature, and this configuration is most likely at high temperature. So here, this probability, it comes from the maximization of Gibbs entropy. You maximize it with the constraint that all the probabilities should add up to 1, and also there's a constraint, another constraint, where we can define average energy. So when you do the minimization here, you end up with the Boltzmann distribution. Now, restricted Boltzmann machines, it's a generative neural network architecture. They are similar to spin glass models because RBMs, restricted Boltzmann machines, accept only binary inputs, so spin up or spin down, +1, -1. But the weights can be anything. These weights can be anything. Since RBMs are energy-based, Boltzmann distribution between the visible and hidden nodes arises naturally. So because these are energy-based models, you get Boltzmann distribution naturally. If I go back to the slide, the reason that you get, again, the Boltzmann distribution is that you can define energy. The same thing happens in these models. There's just 2 layers. So what happens is you have a bunch of people rate these movies, Lord of the Rings, Matrix, Fight Club, Harry Potter, Titanic, Hobbit. So people rate these, they like, they dislike, okay? So what this network does is, just based on the ratings, plus or minus 1, it basically classifies these movies into drama, fantasy, and science fiction. So the probability distribution here is the Boltzmann distribution. It's basically, it gives you, let's say someone, so you train the network and then someone comes, makes this rating for these movies. So this probability distribution tells us that given the rating, this rating, what is the probability that the person likes fantasy or, let's say, drama genre? So these networks, so you can see the connection between the machine learning and physics here. Now, let's move to autoencoders. So unsupervised learning method of autoencoders are useful for finding latent variables. 3 minutes, okay. Okay, thank you very much. So you can train the autoencoder. It's a neural network with real faces. And so the way that you train autoencoders is the input and the output are the same. And then what you look at the hidden layers, and they give you eigenfaces. So what are the fundamental or the basic building blocks of these faces? So it basically gives you eigenfaces. So step 1, train the autoencoder, learn the main features of the data, encoded in the hidden layer in the middle, which is middle layer. So, and then you can, if you want, you can use this model as a fake image generator. So you take this part of the model, you provide some random noise here, and it generates fake images. These people never existed. They're just fake images created by the generator. So now with my student, we were wondering if we can use it, apply it to Ising model. So we simulated the Ising model at finite temperature with Monte Carlo. So we took samples 4 by 4 Ising configurations for different temperatures, and then we so this is 4 by 40 by 40. We flattened them to vectors 1/1600. And then we trained these configurations. We trained this autoencoder with these configurations by using the configurations in the input and output layer. And then we looked at the hidden layers. Now, here's the result. When you look at the hidden layer, hidden node, the second hidden node, its value jumps at, this is the temperature, at 223 at this point. So the exact solution of Ising model gives phase transition, so at 227. And this is the exact result, and our network finds the critical temperature you can compare them, it's 2% error. This is pretty amazing. So autoencoder here was only fed the Ising configurations, not their associated temperatures. So we don't give it the temperatures. We know which configuration corresponds to which temperature, but we don't give the system, the autoencoder, the temperatures, but it can find basically the phase transition point in 2-dimensional Ising model. So let me finish with 2 more slides. So convolutional neural networks are used for image recognition. So you basically have filters, and activation and pooling. Pooling it's a coarse graining, it's zooming out or downsampling, integrating out fine details and leaving out the large scale structure. There are different poolings, max pooling, average pooling. In fact, we do this in when we do block spin in physics. So max pooling is basically take the maximum number, average pooling is basically take the average. So in physics, this is related to renormalization group. It's used to discover the scaling laws, power laws that quantifies quantities like specific heat, correlation length, and magnetic susceptibility. So the change of free energy by averaging or pooling spins tells us how thermodynamic variables change at temperature close to the critical temperature. Here you can do the block spins and you can run the renormalization group procedure here. And finally, let me flash this slide. If there are parties interested in the connections between machine learning and physics, they can look at these books and reviews. So thank you very much for giving me this opportunity, and thank you, I thank the organizers.
Thank you very much for a nice presentation, Şenol. Is there any questions? So I can ask one more question, Şenol. Did you look at next neighborhood in the Ising model?
In this case, no. It was just next neighbors. We haven't looked at NN neighbors, so that can be done, and I think that would give you again the problem. My guess is again the phase transition, shifted phase transitions in that case as well.
Thank you. From Sergey, thank you very much. Very nice, interesting talk, he said. So,
thank you, Sergey.
We can, the next speaker is Faruk Mihevar from University of Innsbruck. Faruk, would you please share your presentation?
Can you see it?
Okay, thank you. Thank you. And
I have a problem with annotation, so I will just, I won't go to the full screen, but it should be, I think, clear.
Maybe you can push to play.
Yeah, but then I
Button.
cannot use the annotation, so that is the problem. Yeah, so then I don't have the annotation. So I will just use in this case. Do you see it or not?
No, I can see you. No problem.
Yeah, sorry, because annotation is not working in the Zoom, so I will just use this one. Well, thanks for the organizing for giving the opportunity. So the focus of my talk is the cavity-induced dynamical gauge potential and its physical consequences. So, okay, yes. So reaching the quantum degeneracy in atomic gases has opened a new direction in many-body physics. So for instance, so by loading the ultra-cold atoms into optical cavities, to the optical lattices, one can mimic solid-state crystalline material. And one of the most notable observations in this setup was the superfluid to Mott insulator phase transition. However, these quantum gases suffer from one major drawback, and that is they are charge neutral, and they cannot couple to the gauge potential that charged particles do. So this basically limits the amount of the phenomena that one can explore in this system. But that said, a plethora of proposals have been put forward to simulate the gauge potential for ultra-cold atoms. So almost a decade ago, synthetic spin orbit coupling and synthetic magnetic field were realized for the ultra-cold atoms. In particular for this, for synthetic magnetic field. So the natural hopping of the atoms between neighboring sides of the optical lattice is suppressed by the energy offset between the adjacent lattice sides. And then this hopping is restored by 2 photon processes. And this process basically imprints phase phi into the wave function of the atoms. So by doing this, so this basically simulates the Aharonov-Bohm phase of a charged particle in a magnetic field. Again, it was noted that there is another setback in this simulated gauge potential, and that is that so these gauge potentials are static and background potentials. It means that so the state of the atom doesn't change the state of the atom doesn't change the gauge potential, and this is quite different from the scenarios that one encounters in a quantum gauge theories or condensed matter. So there, the gauge potential is a dynamical degree of the freedom of the system. So motivated by this, again, another generation of gauge potential, a proposal for another generation of the gauge potential have been put forward, and to simulate a dynamical gauge field for the atoms. So most of these techniques, most of this new generation of techniques are based on Folakate engineering. And recently, density-dependent dynamical gauge fields have been realized for the atoms. So at the same time of these progresses, people start to ask if it is possible to engineer a dynamical gauge potential based on different techniques without restoring to the Folakate engineering techniques. And it turns out that the answer to this question is yes, and it relies on a strong atom-matter interaction coupling. So in free space, the probability of an atom-photon interaction is much, much smaller than 1. So this means that one needs many atoms and many photons to see a nonlinear effect. However, if the radiation field is confined within a cavity, so the photon travels many times inside the cavity before leaking out of it. So this increases the atom-photon interaction probability significantly and reaches almost 1. So in this regime, a single atom and single photon is enough to see a nonlinear effect. So if the gauge potential is induced by the cavity photons, so then this would be the sensitive to the state of the atom. So if the state of the atom change, this would affect the gauge potential. And this is the basic idea behind the cavity-induced gauge potential. So, for example, recently we showed that dynamical spin-orbit coupling can be induced for a Bose-Einstein condensate inside a single-mode cavity by using two independent Raman channels. So we showed that exactly as one expects. So dynamical spin-orbit characteristic appears in the band structure, and this band structure actually are dynamic. So as a consequence of this dynamical spin-orbit coupling, we showed that interesting spin textures emerge in the system. And immediately afterward, so this scheme was realized in the Benlev's group in the Stanford. So I have to now go to this here. So, and as we predicted, they exactly see that the spin-orbit coupling emerges beyond some critical threshold strengths, and the characteristic spin-orbit coupling, the characteristic momentum distribution of a spin-orbit coupling also emerges in the system. So, and now in our current work, so we decided to implement a density-dependent dynamical U1 gauge potential for atoms based on a simple cavity QED setup without restoring to this Folakate engineering. And then we investigated the physical implications of this cavity-induced dynamical U1 gauge potential. So let's start with our proposal. So we consider two components atoms in an external optical lattice. In an external optical lattice, which is perpendicular to the, so again, I will go out of it, which is not possible. So, which is perpendicular to the axis of a two-mode cavity, So in particular, as you can see in the right side, so sorry, I cannot use the notation, so I will just, so as you can see in the right side, in the top figure, so if the atoms are in the lower state, they can absorb one photon from the laser A, shown with omega A, and re-emit it to the cavity denoted with JA, and then move to the right. And if they are in the upper state, spin-up state, they can absorb one photon from laser B, shown with omega B, and then re-emit it to the second mode of the cavity, shown with the GB, and then move to the left. So this is shown schematically in the lower figure in the slide. So as you can see, and then another third laser basically couples this spin up and down on side. So this system is equivalent. So this system is equivalent to a two-leg Bose-Hubbard ladder threaded with a cavity-induced synthetic magnetic field. So as you can see in the figure, so the current in the the counter-propagating currents in the two legs are proportional to the photon number in the corresponding cavity modes. So in particular, the current in the lower leg is proportional to the photon number in mode A, and the current in the upper leg is proportional to the photon number in the second mode B. And the phase imprinted into the wave function is given by the phase of the photons, phi A and phi B. So as you can see in this formula, phi A and phi B, the phase of the photons, are in turn a function of the photon decay rate, palm cavity detunings, atom-photon coupling rates, and atom numbers. So when the atoms traverse one placket of this ladder, they acquire this, they feel this this magnetic flux phi B, which is proportional to phi A plus phi B, and the currents and the chiral and particle currents are related to the total photon number in the two modes and the photon number difference in the two modes. But the most remarkable point is that, so the phase of the magnetic flux, which is proportional to phi A plus phi B, is affected by the optomechanical back action, which is a function of a average density, which is basically proportional to the average density of the particle. So this basically results in an average density dependent dynamical U1 gauge potential, and it has very significant consequences, as I will show in the next slides. So first, we explored the single particle physics, where n is 1. The total number, we have only one particle in the whole system. In this case, this optomechanical back action is quite small, and one can ignore this one and basically reach static gauge potential limit. So we identified 3 different phases based on the single particle energy dispersions and the corresponding atomic currents. So if we have a single minima, so we identify a single minima in the energy band, we identify this one with the photon balanced Meissner state. So which is shown, the currents are shown. So the currents now are shown in here. So this is similar to the Meissner effect. This is similar to the Meissner effect, where in the superconductor, where the magnetic flux is screened by the currents. So it is the same thing in here. So one can imagine that there is a fictitious current going up and down, and this would generate a circular current which would screen the synthetic magnetic field. Then, so if we have 2 minima with 2 minima, so we identify this one with a photon balanced vortex state. This is shown in here. And finally, we identify a photon imbalanced bias ladder phase. In this case, in addition to the pure chiral current, there is also a particle current, as there is non-zero photon, as the photon number is not the same in the two mode, as you can see in this figure. So then we characterize the phase diagram. So we show the phase diagram in this, in the detuning versus the atom photon coupling rate plane. But the interesting physics appears when we go to the many body case. In this case, so this optomechanical back action becomes really important, and as we expected now, so as we expected, the magnetic flux now depends on the density, average density. So the background color in this figure, in this phase diagram, is the magnetic flux, and as you can see that it depends in the average density. But interestingly, we also identify a regime with a nonlinear dynamics. So then we took a closer look to the physics in this nonlinear dynamic regime. So interestingly, we saw that the fields display periodic and time-dependent behavior in the phase space. So this is the mode A and this is the mode B. As you can see that, so this is a long time. So this figure shows only the long time behavior. So it shows a periodic behavior. So it is as a consequence, so the phase of the fields so changes periodically in time. So this means that if you remember, so the magnetic flux is proportional to the phase of two modes. So as a consequence, so the magnetic flux changes in time. And as we know from the elementary electromagnetic physics, if the magnetic flux changes, this would induce an electromotive force. And we know again from the electromagnetic, so electromotive force results in a currents in the system. Since in this case, electromotive force is time periodic, so you could see that the chiral and particle currents also exhibits a periodic behavior. So, and again, interestingly, so we see that in some parameter regime, the second harmonic also emerges. So this means that now we have a double period doubling situations. So with this,
last 2 minutes.
Yes, I'm almost done. So with this, we show that one can simulate a Faraday's induction law for neutral particle using a dynamical instability in a cavity-induced dynamical gauge potential. So, and with this, I come to the conclusion, and so we showed that average density dependent U1 gauge potential can be simulated with cavities, and then as a result of dynamical instability in this system, Faraday's induction law basically emerges naturally in this case. So now the question that we are exploring and we are asking ourselves is that could we identify this periodic behavior and this emergence of a Faraday's law as a kind of a time crystal? Because this periodic behavior breaks the time translation of the system. And if we go even to higher atom photon coupling rates, we see that even more harmonics are appearing in the system. So this basically implies that we might have a chaotic behavior. And this is not very surprising because any period doubling would naturally lead to the chaotic behavior. So with this, I would like to also say that this work has been done in collaboration with Elvia Colella and Helmut Riesch at University of Calgary. And most of the calculation that I showed today, it was done with Elvia. And at the end, I would also like to draw your attention to our recent review paper in cavity QED with quantum gases. So if you are interested about the state of the art in cavity QED with quantum gases, you can consult this paper. So we give a quite pedagogical review of the field. So with this, I would like to thank you all, and I would be happy to answer any question if you have.
Thank you for presentation, Faruk. Are there any questions? Or is there any question? No question.
Okay.
Okay, so thank you again. Thank you again. I forgot to say something about the session will be live streamed over YouTube. So we can. The next speaker is the last speaker, İskender Yalçınkaya from Czech Technical University, and he will talk about disorder-free localization in quantum walk. And please, İskender.
Thank you. Thank you for your kind introduction. I hope you can hear me and you can see my screen. And now it's full-sized.
Okay.
Yeah, thanks for your introduction. I would also like to thank the organizers for giving me this opportunity to speak in this workshop again. In my talk, I will tell you about one of our recent works, which published recently, actually here. It has the same title as my talk. It is disorder-free localization in quantum walks. To be honest, since our ideas took a lot of time to mature, our paper involved many ideas, as you can see here, but I'm not going to talk about all of them. I'll just follow this safe trajectory. I'll first introduce quantum walks from a conventional point of view. And then I'll describe quantum walks interacting with a spin environment, which is actually our model we considered in this job, in this paper. And then I'll directly jump into some of our results about localization without explaining any mechanisms behind them, because these localizations are regarded as disorder-free localization in literature. But before I come to there, I need to tell you about disorder in quantum walks, some disorder schemes in quantum walks. And then I'll describe why we obtain these localization effects. And if I have some time, I'll tell you about how our work is related with many-body localization from the point of view of this spin chain. These are my collaborators. I also would like to thank each of them sincerely for their cooperation during this study. What are quantum walks? They were introduced almost 30 years ago as the quantum counterpart of classical walks. They are called counterpart because a quantum walker takes a step in the same way a classical walker does. We first toss a coin, then we move the particle according to the coin state. But since we are talking about quantum mechanics now, our coin state, our coin is a two-dimensional quantum system. And our coin toss operation is actually a unitary operation I wrote down here. And the coin operator directly acts on the coin space. It simply rotates it simply rotates the state of the coin about the x-axis by an angle of theta, and we chose theta pi/4 in our work, and it doesn't touch to the position space at all. And then we move our Walker according to the coin state. If we have a 0 state, we move the quantum Walker to right. If we have 1, we move the quantum Walker to left. And we repeat these actions, these 2 subsequent actions, and we call both of them as a step. We first apply a coin operation, which acts on the coin space, and then we shift the position of Walker according to the coin state. This W defines a step of the quantum Walker. So starting from an initial state, after the application of, say, 100 times, if we apply this coin step operator 100 times, this is the probability distribution we get, indicated by blue line here. And I also drew this probability distribution of a classical Walker just for a reference. A quantum walk spreads quadratically faster than classical random walk, and this is advantages in some search algorithms and so on. So what do we have in addition in our model? We have exactly the same quantum walk model, but now we associate spin 1 over 2 particles with sites in our space. So in each position, we also have a spin 1 over 2 particle or a qubit in a general sense. So after we take a step by C and T, by coin operation and translation operator, then our Walker interacts with the particles, with the spin 1 over 2 particles at that particular position sites. And the nature of this interaction is the quantum Walker just rotates these particles around about x-axis by an angle of phi. Okay, and we call this parameter as our interaction parameter. And it can take values from 0 to pi, and I'll describe its importance in a bit. Is there anything that I skipped here? Of course, we iterate this. Now our step operator has become WM with an interaction with the spin chain or with the spins at every position. And we iterate the step operator again and again to govern the dynamics of our quantum walk, our model. So what do we obtain with this scheme, with this interacting with this quantum walk scheme interacting with the spin chain? This is the energy diagram. This is the quasi-energy diagram of our step operator. And these are the quasi-energies, and this is our interaction parameter. The quasi-energies are 2 pi periodic because of the discrete nature of the step operator. It's similar to quasi-momentum. If we have a discrete space, then we obtain quasi-momentum. And in this case, we have a discrete time evolution operator. And that's why we are getting a 2 pi periodic energy diagram. And if there is no interaction, we obtain all our eigenstates delocalized. By the way, and these colors represents inverse participation ratio of the particular eigenstates. So if the inverse participation ratio 0, then we have a complete localized state. If it's 1, we have a delocalized state. It's uniformly distributed along the lattice. If we have no interaction and we turn back, we obtain the conventional quantum walk. And this is the energy diagram of a conventional quantum walk. All eigenstates are delocalized. As we increase the interaction parameter, we see that these band gaps start to close. And they are completely closed at this particular phi interaction parameter value, 1/4. And then we saw that almost all of the eigenstates are localized. Of course, we obtained this diagram for 18 spins for 18-dimensional position space accordingly, and with periodic boundary conditions. And we solved, actually, we solved this step operator exactly. I mean, I obtained the spectrum exactly. And is there anything? We also, I would like to indicate that all delocalized states are gathered around the band gaps. So we see a localization, and these are some of our other results. And this is the probability distribution of the quantum walker on the position space after 400 steps. If phi is 0, we obtain this conic distribution, probability distribution of quantum walker. And as we increase the interaction strength, we started to get more and more localized probability distribution. And after we pass this 1/4 threshold, our probability distribution is exponentially localized. And this is the variance of the probability distribution with respect to number of steps. Again, we see that first ballistic behavior, it's the signature spreading behavior of quantum walks. It spreads, its variance changes with respect to time with this, it's ballistically. And as we increase the interaction parameter, and we see that this spreading starts to stop. And after 1/4, after phi 1/4, we completely get actually sub-diffusive behavior of sub-diffusive spreading of our quantum walker. And this is the inverse participation ratio values with respect to interaction parameter. Again, we see that our particle is localized after 1/4. And this is just another representation of the change of variance with respect to the interaction parameter. Again, the variance drops drastically after that threshold of our interaction parameter. Well, I explained we obtained some localized results if we consider such a model, but I didn't explain why do we get it. Before I come to that, let me just talk a bit about disorder models in quantum walks. Actually, there are a zoo of different disorder models in quantum walks, for quantum walks in literature, and I'll tell you about only one of them, which we studied earlier. And they can introduce disorder to quantum walks by just preventing quantum walk to go to a site. It's called broken links, and they can introduce it by just defining a different coin operator for each step, or they can also define it by just assigning a different coin operator for each position. But in general, we can classify all these disorder models into two categories. They either break temporal symmetry or position symmetry, translational symmetry. If we consider our first case here, this is completely temporal and positional transitional symmetric. We always apply the same step operator in each step, and particle doesn't coincide with something different in different positions. If they break the symmetry, then they obtain kind of disorders or bound states. And that's what we obtained in this paper. This is probably the simplest disorder model for quantum walks. Again, we have the same quantum walk model, but we apply the coin operator, translational operator. Then we put some phase to the quantum walker if it steps on the origin. In each time it steps on the origin. Okay, whenever it's I think I did a mistake here, but this should be, I mean, this is different than 0 if n is 0, and it is 0 for this. Yeah, I forgot to write that, sorry. So quantum Walker gains a phase whenever it steps on the origin. In this case, and this is the phase obtained by the quantum Walker, I indicated with e to I psi. And this is the position space, and the colors indicate the probability of finding the Walker at that particular position. And this is this psi parameter in the vertical axis. We see that for most of the values of the psi, the quantum Walker is localized at the origin mostly, but it also has some distribution. It has some, it spreads, I mean, we see some bound states at the origin, but some eigenstates are still able to distribute, spread among the lattice.
İskender hocam, time is up actually. Could you please?
Okay, let me just explain what's happening in 2 minutes. Is that okay?
5 more minutes you can.
Oh, I have 5 minutes.
No, actually, time is up, but you can 5 minutes.
Okay. I'll this was my last slide, and so why do we obtain these localization results? Let me explain it lastly. Assume that we start from an initial state, and this represents the coin state, and this represents the position state, and this represents the state of the spin chain. And let's assume that we start from this particular state. Okay, an eigenvalue of z, Pauli z operator. And we can write this spin chain state in terms of plus and minus. I mean, the eigenstates of X operator in this way. So we can write the whole state as a superposition of 2 to n possible spin sectors. Okay. So whenever we apply, because we apply the coin operator, it only affects the coin space. We apply the translation operator, it only affects the position space depending on the coin state. And then we apply our rotation operator, the interaction operator M. And watch that, note that this operator affects these states separately. I mean, it affects the spin sectors separately, independent from each other. So each spin sector evolves in its own. In a way that whenever we apply this M operator in this sector, for example, or let's say in this sector, the quantum Walker possesses a phase of e to minus e phi. And also for this sector, it receives a phase of minus e to I minus phi and e to plus phi phase. So each spin sector evolves in its own disorder scheme, as I already pointed out here. So which means that we can block diagonalize the step operator with 2 to n blocks, and we have 2n and 2n blocks, and we have 2 to n possible blocks like this. And each of these blocks evolve the quantum Walker in its own sector with its own disorder scheme. And we can see that if we want to calculate the probability distribution of the Walker on the position space, we see that it's equivalent to taking an average over all possible disorders we see here. And so the probability of finding the Walker at a particular position at time t becomes an average of all possible disorder schemes we obtain in the sectors. So that's why we obtain a localization as we did here in this slide. But of course, now we have a more complex and the localization of our part, the dynamics of localization of our particle is more rich. So I'll skip this slide. Here we also considered the dynamics of spin chain, and we saw some signs of many-body localized phase if we calculate the von Neumann entropy of the spin chain, so the half of the spin chain, but I don't have enough time to represent them. These are our techniques. Well, I don't need to talk about them too. So thanks for attention. I already exceeded my time. So thanks for your attention and for your understanding.
Thank you for your talk, Iskender. And I would, on the behalf of the organizing committee, I would like to thank all the speakers in this section that they contributed to the quantum optic meeting. So our last session will be started at 4 p.m. So reconnect please at 4 p.m. Is there anything I need to specify, Ceyhun Hocam? Oh, is there any questions? So one more question. Iskender, are these conclusions beyond QW and extends to continuous works too? Are these conclusions beyond quantum work and extends to continuous works too? From
Are results applicable to continuous time quantum works? Is that the question?
Yes.
Well, I did I understand it correctly?
Yes.
Well, to be honest, I have no idea because I didn't make any calculation in that direction. So I don't know, but continuous time quantum works don't have any coin state, and our technique, our model takes its power from this coin state, and I'm not sure how to apply this model for continuous time case. Actually, I can't see it in the first place, but maybe there should be some way to do it, and we can define another model, or we can do some trick to. But our model takes advantage of these coin states, and that's why we get these, in some sense, get these localized results. And I don't know what would happen in continuous time case. I hope this answered your question.
Yeah, I hope so. One more question. Another subsystem can play the role of the coin. From Özgür Müstecaplıoğlu, Professor Özgür Müstecaplıoğlu, I guess. Thanks.
Oh, is this a comment or question?
Comment, yes, comment, I guess.
Another subspace could play the role of the coin state.
Yes.
For the continuous time case, or for I couldn't quite get the comment, but can I see them here?
You can see it in the chat platform.
Well, somehow I can't see it. Where is the chat? But maybe if I stop my sharing, I can. Now I can see it. Yes, Are these conclusions beyond quantum walks and extends to quantum from Özgür Hoca, and another subsystem can play the role of the coin? Oh yeah. Okay, now I got it. Yeah. So the second one is just a comment.
One more question from Theodora. Please, Theodora.
Sorry, I don't know much about quantum walks, but can you use your model for describing like natural processes like photosynthesis or transfer of some energy and charge?
Quantum walks are widely used to describe this kind of phenomena, especially the photosynthesis process, and they use both continuous time walks and discrete time quantum walks for that purpose. As far as I know.
Okay, thank you.
You're welcome.
Okay, so thank you again. I would like to thank all speakers in this section for their contribution to the quantum optical meetings. So our last session will be started at 4 p.m. and please reconnect at 4 p.m. Ceyhun Hocam.
Yeah, we have to change the YouTube URL each time. That's the reason. Sorry for the inconvenience.
Okay.
Thank you.
Thank you. Thank you very much.